Okay, guys, so let's get started. So we will be solving quite a few problems. So let's see how much we can solve. So we'll start with an easy problem. Okay. So let's start with this one. So we'll delete this, whatever it is, and let's see. So we have a fair die, six-sided fair die, and we roll it twice. The question is to calculate the probability that the first roll is strictly less than the second roll. So I am going to teach you guys, since it's an easy problem. So in our course, what we have developed is we have easy, medium, hard, and easy problems are where we things teach from scratch. Medium problems are we assume the ideas and like we share some use those theorems and results to solve the problem. And hard are those high those niche techniques other than just knowing the theorem, like recursion and all those things. This is the structure in classical probability and combinatorics, and similar is the structure in other cases of problem. So easy, since it's an easy problem, we will be teaching you how to think from scratch. So you roll a fair six-sided die twice. So what is the sample space of it? That's the first question. What is the sample? So what is the experiment first? Again, experiment E, or experiment is nothing but the outcomes of, or it's a two fair die, right? Six-sided, remember that. All of you can see my screen? Yes or no? All good? Okay, good. Next, it's an experiment, right? So we will have an outcome of it, the space of outcomes. It's called the sample space. Sample space S, which is nothing but, let's write the math of it. So we write the maths of it because it's easy to write. You should learn to write. So you will see what I mean. Okay, so I comma j, all the pairs is that I comma j is in 1, 2, 3, dot, dot, 6, right? That are the outcomes. So this is the sample space. Now let's look at the required event. Every event, we can only find probabilities for an event, which is a subset of the sample space, a good subset. So the required event E is nothing but, it's of course this will be there, this condition will be there because it's a subset, plus something. So here we will have another addition, something that we don't know, which we are writing like this, plus I is less than j. Okay, this is what we want to find. This first roll is strictly less than the second roll. All of you got it, guys? Can you give a thumbs up? This is an easy problem, guys. We will be going to harder problems very soon, don't worry. Okay, great. So now the next is finding the probability. So as you can understand, this is a classical probability problem. So why? Because each of the sample space elements, why classical probability? This is classical probability because each sample element is equally likely because of the fair coin condition. This will also teach you how to write solutions, right? Because of fair die assumption. Okay, so now therefore, if it's in this classical probability, we can write P of E. Probability of the event E is nothing but, you can write as the number of elements of E divided by the number of elements of S. All of you can see the equations, guys. I hope it's not too short for you. Okay. So now number of elements in E divided by the number of elements in S. So you already know the number of elements in S. The number of elements in S is how much? By multiplication theorem, but it's a Cartesian product, right? It's 6 into 6. Right? And the number of elements of E is what we need to count. And this is where we need the trick, an interesting trick, an idea. We can easily count, of course. You can easily count that if J is equal to this, what will be this. But I mean, you can easily count, of course. Okay. So if you want to count, you can see that if you can sum it up into different cases. You can sum it up like you can write E as E with J is equal to. So we are now using what is called we are disjointing. We are making this. It's a kind of tree diagram. It's like we are making a disjoint, right? So if you want to draw it, it will be something like this. If you want to draw it, it will be something like this. So let's say E here, and E will have, I have all set up for you guys, don't worry. E with J as 1 divided by E plus E with J as 2. J means the second rule. 3 dot 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 E with J as 6. Okay. So we'll have all these conditions out here. It's kind of a disjoint subset, disjoint set. E is divided into these disjoint sets. This is what I mean by a tree diagram. So you can clearly understand this is a disjoint, and hence you need to sum it up, right, guys? So you can do like this, and you can find out that E is therefore, if J is equal to 1, if J is equal to 1, I has only 0 options because I should be less. So 0 options here counts. If J is equal to 2, then I has 1 option. If J is equal to 3, I has 2 options. Or if J is equal to 6, I will have 5 options. So the sum will be what the solution is, N of E. The sum is what we are looking at. Okay. And therefore the sum will be 1 plus 2 plus dot this, which is nothing but 5 into 6 by 2. Right? Which is easy to understand. All of you got it, guys? This is one way of doing it. So these are disjoint information we're using at something called addition principle. Any question? Sorry. Okay, any question, guys? I cannot see the screen though. Okay, all good? So this is addition principle. Okay, so we can do, one way to do is like this. That's also possible. So we can solve like this. So this way we can say it's 15. By, we can say that it's 15. But there are other ways to do it, what I'm saying. And this is what I'm talking about, symmetry principle. So the idea is that, and this is what it's a bit algebraic. So the idea is that the sample space E, so the entire sample space S, observe this very carefully now. The entire sample space S now can be written as, oh, perfect, Ujjwal. Yeah, but one should also know multiple ways to do it. This entire sample space can be written as now in three different ways. In 3 different ways. The first way is this E. E is already there, right? Required event E. And if you observe that E complement is nothing but, so we can have this 3. E is equal to this with the given condition that I is strictly less than J, probably. Yeah. The next one is I is therefore greater than j, and the third is I equal to j, right? This three. Now the beautiful thing is that let's call it f and let's call it g. The beautiful thing is that by symmetry, this e, n of e should be equal to n of f, right? Because I and j are interchangeable, because they are fair die, they're independent die. You do not know, like both the probability of I less than j and I greater than j are the same. It's kind of you replace I and j variables. So what is happening? So n of s is nothing but n of e plus n of f plus n of g, right? And what we'll get from here is that therefore n of s is nothing but twice n of e plus n of g, right? And then we already know it's 36 n of s twice n of n. N of g is what? How many I and j are there pairs as I is equal to j? It means I comma I, and I is only between 1 to 1 is between 1 to 6 through 1 to 6. So n of g is nothing but 6 options are there. So we get that n of e is equal to 30 by 2, that is 15. Make sense, guys? All of you? So this probability will be 15 by 36. Okay. All of you understood this, guys? Yes or no? Any questions? All of you understood this? Questions, guys? So this is the fundamental part. So this is how you solve it. So if you understood this problem, that means the solution, that means you are good with the fundamentals of probability space and axiomatic probability, because we have used here, or rather, yeah, we have used here this whole idea that it's the probability is summing up, or the number of counts of e is summing up, right? So it's nothing but an application of probability. So this will really test your understanding of probability. Okay, all good, right? Can you give a thumbs up, guys? All of you here? Any questions? Time to drink my coffee. Okay, perfect. Next question, guys. So, do you want a medium one or a hard one? Do you want a medium one or a hard one? Or another easy one? Okay, how many medium, how many hard? Okay, 2 mediums, 1 hard. 3 mediums, 1 hard. Okay. Okay. So most of them are medium. So let's try a medium problem. Okay. This medium problem is actually very, very interesting. Yeah, this is very interesting. So please stay with me, guys. So it's asking the very first problem. It's asking how many permutations. This is a very interesting problem. How many and you will learn something new here. I'm telling you, you will learn something new here. So no, there's no step by step Shumit here. It's like I solve these problems and I go from easy to medium and then hard. Okay. So let's solve this problem. How many permutations are there such that of between 1 to 7 of 1 to 7 such that they have no adjacent event digits? Beautiful, right? So first of all, whenever you're solving this problem, guys, first step is always to take an example. See an example, guys. For example, 1, 2, 4, 5, 6, 7. This 3 is not possible because 2 or 4 are like not possible, right? But another example is 1, 2, 5, 3, or 5, 6, 3, 4, 7. This is possible. Yeah, someone said something. Let's see. Someone said something. Let's see. Okay. So it's a one possible. So always step one is take examples, because examples will make the path for your understanding that what you should do next is how many permutations are there. In general we have seven factorial permutations, right, 7 factorials, each one for each place. So in case you do not know this, how factorials or permutations are done, for the first place there are 7 options, for the second place, like for the first place is second options, for the second place 6 options, for the third place 5 options, for the fourth place 4 dot, 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 till this last 2 place 2 and 1. And that's how you get, by multiplication principle, you get 7 factorial, 7 into 6 into 5 into, this is the 7 factorial permutations. Okay, so the question is that we have no adjacent event digits. So somehow we have to choose that where the event digits will sit. Okay, and this is a very important technique. So this technique called non-adjacency algebraic technique. And this should come naturally to you. So what the technique says is this, that how to make sure that you choose numbers that are not, how to make sure that you choose numbers that are not adjacent. Okay, so one important thing to note here, how many even numbers are there? How many even numbers? There are 2, 4 and 6, 3 even numbers, right? So the thing is that how should you place the even numbers? So observe this very carefully, guys. This factorial, how can you count this factorial? You can count this factorial in this way, that out of these 7 places, understand this very carefully, you can also count this way, this permutation. The 7 factorial permutation can also be counted in this way. First choose the places of even numbers, then permute. So this can be step number 1. So 7 factorial can also be got by first choose the places of even numbers, then you permute those even numbers, and then you permute, because if you choose the places of the even numbers, automatically the places of the odd numbers are fixed. So imagine in your mind choosing first the places of even numbers, then permuting them, and then what is left is, whatever is left, it's odd numbers. So you know it's odd numbers, just have to permute now. Permute odd numbers, right? So these are the 3 steps. So for the choosing the even numbers, it's 7C3, right? 3 even numbers. For permuting those even numbers, 3 factorial. And for permuting those numbers, 4 factorial. So there's 7C3 times 3 factorial times 4 factorial. And if you observe it carefully, it's 7 factorial by 3 factorial times 4 factorial. 3 factorial, 4 factorial gets cancelled. So you have 7 factorial. All of you got this. Is very important, guys, to solve this problem. Did you understand this, guys? Yes or no? How does this 7 factorial come up? Okay. So now, any questions, guys? Because I would like to help you all. If you have doubts, please ask me your doubts. That's why the live class is for. Ujjwal, Ishan, Anisha, Ankit, Arjun, Bonda, Farhat, Kabir, Mahavidya, Priyank, Shakti, Siddhant, Sindhuja, Srini, and Shumit. Any questions? Do not think that you are stupid to ask questions. Most intelligent people ask more questions. Okay. So Anisha, you are in the course. So any questions? Okay, all good, right? Everything, the explanation is going great. I hope it's clear all. Okay, good. Yeah, because this will be used for the other course people. So I just want to make sure that they are pitch perfect, the best training ever possible for probability. So okay, so now observe that where is the now? Can someone tell me where is the change going to take place? Which place there will be the change? Which place do we need to change, guys? Among these three steps, three sequential steps, which yes,
7C3.
exactly. So we need to choose the event places properly. That's where it needs to change. So can we choose any random place? No. So the question therefore turns out that how to make sure to choose even numbers, three even numbers, three places. No even three places that are not adjacent. That's the question it boils down to, guys. So this is the question it boils down to. How to choose. This is the question it boils down to. All of you got it? This is very important, guys. Very, very important. All good? Okay. So now the question comes that how to choose three places out of seven places that are not adjacent. And this is where we use the NAT technique, non-adjacency algebraic technique. So why I am called algebraic? Because how do we choose places? Let's assume we choose when we choose places. Let's say we choose three places out of seven. We say 4, 5, and 9. Let's say, or three places out of 10 places. So 4, 5, and 9. So we have some x1. So we have some x1 less than x2 and less than x3, three places, let's say. So the way to choose any three increasing numbers is equivalent to 7C3. Anyways, let's not go in there. So we are choosing x1, x2, x3 increasing, but we cannot do it now. We cannot do it anyone. So how to make sure that x1, x2, x3 are not adjacent? Yes. I will see whether you will get this notes. I will try to give you notes, yes. But ideally, everyone should take their own notes while live classes because that's how you learn. If you're not taking down notes, you're not serious in the class. So that's the whole idea. You can watch the video later on when we publish and then take down notes because you learn the best when you take notes, guys. If you're not taking notes, probably you're not serious. You're just here for entertainment. Okay, you're here for entertainment. I don't care. But I'm sure there are some serious people out here. Okay, so how to make sure x1, x2, x3, which are increasing. Sorry, can you mute yourself? There's some background noises. Srini. Oh, you have some questions, Srini? Or something you want to say?
No, I thought you were asking us the question.
Oh,
Sorry,
no,
sorry.
sure. You go ahead. If you have ideas, please go ahead.
Okay. Um, you have four odd numbers, and you drop the even numbers in between those odd numbers. So
No.
in
See,
between those odd,
we
so
ask.
you have like five slots, right? You have, if you write odd, then you have five slots in between those odd numbers. And so I need to choose three slots amongst them to drop even numbers in.
No. I am asking you to just answer this question. Okay. There are many ways to solve this problem. One of the question I'm asking is if you have how to choose three numbers out of n numbers like x1, x2, x3 says that these three numbers are not adjacent. Forget about even and odd because we are reducing the problem to choosing three numbers that are not adjacent.
So we can choose three numbers like the difference between any two number should be greater than one or greater
Yes.
than two.
Very good. So how do you make sure, how do you mathematically represent? That's a very good idea. How do you mathematically represent that? That's a very, very unique, very minute, very delicate trick out there that we will do. Any ideas? So we will just make some changes to x1, x2, x3, just minute changes. Instead of choosing, yeah, that's true. But think in terms of how can you change the algebra of x1, x2, x3 to something different, such that this, though positions are never, so position of the first even number or is the smallest, like the smallest position is x1, the next position is x2, next position, then the third position is x3, in increasing order. The question is that what minute algebraic change can you do to this x1, x2, x3 such that these are never consecutive? Because if you choose x1 and x2, there may be a chance that x1, x2 are consecutive. So what to do to this x1, x2, x3 algebraically so that they are never consecutive? That's the question. Do you see the thought process?
So like creating difference of one greater than one
How
can be
how
one of the approach.
how?
Sir, we can transform like x2 equals to x1 plus 1 or x1 plus 2.
That's close. But that
So
will make x1
because
x. Yes. Go ahead.
okay, so because you have ordered it, you can choose your least element first. That is now x1 because you have ordered x1 less than x2 less than x3.
Hmm.
Now your x2 can be anywhere between x1 plus 1 to the total minus 1. I mean minus 2, right?
That's
And then x3 can be from x2 plus 1 until the end.
right. But there's a better way to do it. So what I'm saying is
x2
that in
plus
the
2
previous,
continue.
so yeah, so thing here is that x1, x2, x3 are kind of independent here. Do you see the point? Like not independent. Like what I'm saying is that x2 is greater than x1. We want to keep it that way, but we want to add something. We want to keep this inequality, but we want to add something. Okay. Let me tell you. But you're all right. The thing is that you are thinking. So the reason is that why we are using this is because the number of ways to choose any three increasing numbers out of seven numbers is also this, is 7 choose 3, because you are essentially, it means that you are choosing three places. Whatever you choose, there will always be an increasing unique order, right? So what we will do is that instead of changing the relationship between x2 and x3 and x1, x2, x3, we want to keep the relationship, guys. What we will do is that we will add x1 plus 1 and we'll add x2 plus x3 plus 2. This is beautiful, right? So if you do this, observe that now these positions, these are the positions now. These are the positions now. Now these positions are never consecutive. Whatever numbers you put in. With this condition, and yeah, less than equal to 7, and observe with this condition, x1, x2, x3, these are never consecutive, right? All of you got it, guys? This is so beautiful, right? Do you see the point? Whatever number you take here, let's take x1 is equal to 1 and x2 is equal to 2. It becomes 1 comma 3. And if you take x2 is equal to 3, x3 is equal to 3, it becomes 1, 2. So 1, 2, 3 becomes 1, 3, and 5. It's never consecutive, right? So what happens is that Now, but there's a condition that x3 plus 2 must be less than equal to 7. That condition should always be held. So it turns out that x3, the maximum element, should be less than equal to 5, 7 minus 2. So what it turns out is, now you have to choose between this. This will hold it. So therefore, the answer is 5 choose 3. Got it, guys? Beautiful, right? All of you got it? It's beautiful, right? So this is the way you exactly. Now the thing is that what you guys were doing was you're making x2 depend on x1, which would make, like, if there are n numbers, like k numbers, it will be k like summations. And it is like that cannot be acceptable. We need to simplify it. Yeah, it's like x. Yeah, Farhad. Yes, questions, Farhad? Anisha, did you understand? Since we are trying to answer. Sumit, did you understand? We proved it, right? What do you want me to prove? Yeah, we proved it, right? So the positions instead of x1, x2, x3, the positions instead of x1, x2, x3 is now the positions of the three numbers x1, x2 plus 1 and x3 plus 2. They are never consecutive. Did you get this point? They're never consecutive, right? So if they are never consecutive, the only way, that means these three positions are there. So now if you choose any number between any, let's take any number between x2, x3, let's say x1 you take is equal to 2, 3, 5. This, if you take x1, x2, x3 as those numbers, it turns out the position of the even numbers are 2, then 3 plus 1, 4, and 5 plus 2, 7. So there is I made a one-to-one relationship, bijective relationship between the positions and x1, x2, x3 between 1, 2, 3, 5. So essentially the whole idea is I am building. So this is what is by building a bijective relationship between this and positions of the even numbers, or rather three places that are not adjacent. How by this result? Makes sense, Anisha and others? Good. So anyone? So you should ask this question. I do not poke you, Anisha, to ask. Let me make you ask this question. You should ask this question right away. Okay. Any questions, Farhad? Yeah. Go ahead, Farhad.
Hello, is my voice audible?
Yeah, you're audible now.
Actually, I've not understood why we have taken this condition. X1 is less than X2. Is this the starting point of your solution?
Oh, why this one?
Why this specific restriction? X3 is greater than X2.
Oh, so okay, that's a good question. So I explained it, but I will explain it again. So when we are choosing three places, okay, when we are choosing three places, let's close your eyes and imagine that out of 7 places you are choosing 1, 2, 3, 4, 5, 7. Out of these numbers, you're choosing 3 numbers, any 3 numbers. That's equivalent to saying that choosing 3 increasing numbers, right? If you take any number, let's say if you take, because there is no order here, right? 5, 7, 6 is same as 5, 6, 7. So whatever 3 numbers you choose, there'll be only one unique increasing sequence, 3 number sequence. So instead of saying that we are choosing 3 numbers, we are now saying we are choosing 3 increasing numbers. Both are same because it's a one-to-one relationship. If you choose
Okay.
3 numbers, the set, it's equivalent to saying choosing 3 increasing numbers. Make sense, guys?
Yeah.
Bharat, make sense? This is a very
Yeah.
important.
Yes. Yeah.
That's why I have made. That's why I wrote this. The number of ways to choose 3 increasing numbers is same as number of ways or to choose any 3 numbers of 7 numbers. Okay.
Okay. Actually, till now I have seen these problems by using that something called as that stars and bars method
Yeah.
of which we do, which actually Sharmi was telling. So that was something which was easier for me to understand what he was trying to tell. But this approach is something which is new.
It's new, exactly. That's why I'm calling it a new method, and it's very important method. There will be a lot of not. I mean, it will not just work for non-adjacent. You can work that the difference between 2 numbers is greater than 2. Okay. If the difference is not just adjacency, means what? Difference between 2 numbers must be greater than or equal to at least 1. If we say that no 2 numbers are like the difference, the position difference should be at least 3, then what we will do instead of x1, x2 plus 1, x3 plus 2, we will do x2. So instead of this, we will do this. Okay. So then you can see that. So this is what will happen if in that case. Makes sense, guys? This is very important strategy. Whenever there is adjacency concepts, you can always use the position of this idea.
Something new.
Yeah.
Thank you.
So this is very important. Yeah. Any questions, guys? All good? New concept? Can you write a boom in the comment box if you like this problem, this new idea? Perfect, Shumit. Perfect. Superb. It's a new concept, yes. So the whole of combinatorics and counting is nothing but finding these very cute little ideas of counting that can really, really be useful for you. Okay. So this is all about bijection. Therefore, I'm calling it bijection principle. It's very important. So, okay. So very beautiful problem, guys. Now move on to the next problem. Okay. So let's try to do how much time we have left. We don't have much time left, but okay. Let's try to do this problem. This is a fun problem. So this is a hard problem. So I will hide the solution. So now the question is, A and B are uniformly randomly selected subsets. So we have solved problem number 1. We have solved problem number 4, and we are solving problem number 6 now. So A and B are uniformly random selected subsets. You will also learn another technique here, which I call coding technique. Okay. So yeah, it's a very beautiful technique here, and you can solve multiple number of problems. So if A and B are uniformly randomly selected subsets of 1, 2, 3, 4, 5, find the probability that A and B are not disjoint. Okay. So let's write the sample space here again. The sample space here is, it's a set of all subsets, subsets of this, right? And they're equally likely because it's uniformly. So probability is classical probability. Because the sets are, 2 sets are uniformly selected. There are no condition that B cannot be from this from the set that A has been selected from. So this is the classical probability because that's okay. So now the next part. So therefore A and B are selected. They're independent kind of. What is the probability in A and B are not disjoint? Okay, are not disjoint. So we will try to understand that when A and B are disjoint. That's the question. And this is something, it's hard, it's not easy to do actually. So I need a diagram to help you out. And okay, so before we solve this problem, let's try to recapitulate or remind ourselves the proof of counting all the subsets of a set. Let's say 1, 2, 3, dot, 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 n. Can anyone, does anyone want to try? How do we do that?
So we can consider power set 2 raised to n. Power set is all the possible subset of a given
Yeah,
set.
so I'm
No?
asking you to prove that. How do you prove that all the possible subsets are is sum is 2 to the power n without using binomial coefficients?
Actually, we can do it by using recursion.
Okay, let's try without recursion.
Yeah, one possibility is that for each element, so there are 5 elements here. So each element has two choices. One is to either to belong to that set or not to belong to that set.
Perfect.
If we do that, then we get it naturally that it is 2 to the power 5.
Perfect. So any subset, perfect. So any subset is nothing but, so for example, 1, 2, 5, it is equivalent to saying that this set, sorry, this set 1, 2, 3, 5, let me write it here, it's better. The 1, 2, 3, 5 is similar to saying that now essentially what we're doing is that we are converting a set into a sequence, an ordered sequence. We are converting a set into an ordered sequence by something called coding, coding the position, coding the position method. So 1, 2, 3, 5 we are converting into convert subsets into ordered set of presence and absence. So what we do is that, okay, one is, so we write, so we take all the elements 1 to 3 dot dot n, and we make one if the element is present, otherwise not. So 2 is present 1, 3 is not present 0, 4 is not present 0, so 5 is present. So it's this. It's equivalent. So the idea is put 1 if the element is present in the subset, 0 otherwise. So what we're doing is that we have a bijective relationship, 1-to-1 relationship, 1-to-1 onto relationship between all such subsets and this ordered sequence of zeros and ones. We also call it binary sequence. Now, how many such binary sequences are there? It's simple. Each place, n pluses are there. Each place has two options, so it's 2 to the power n. So it's 2 times 2 dot, 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 times 2 n times. So it will be 2 to the power n. All of you got it, guys? This one? All clear, guys? Any questions? No, why I chose this method? As Sri said that there are multiple ways to do it, right? But we're choosing this method because it teaches you something very important. Yes, you can also do it by recursion too. So Srini, you can tie it by recursion and let us know in the group, in that enquire group, okay, or others too. But I'm going to teach you one. We will just extend this coding the position method, okay, to this problem. So for this subset, so we'll draw it first. So the thing is that we don't understand this, but if we draw it, it will be something like this. So this is the entire set. This is the entire sample space. So let's, can we get the, oops, sorry. God. how to, anyways. Okay, let's call this the sample space. I wish there was some other, anyways. Just let me just see if I can get back. Just give me a minute. Yes, I couldn't. So this is sample space. Now you're taking a subset. Let's say this is a subset. So now we are counting all possible subsets, right? So observe that an element, so this is a subset, the sample space. So an element, any element of a subset, any element can either be here, outside, or inside, right? Two options, can be inside or can be a part of the subset, or can be outside. Right? So therefore, if it's inside, we are considering it. So what we are doing is, if it's inside, so 1 if inside, we are essentially doing this. 0 if it's outside. So we are essentially doing this. This is how we are counting. All of you got this, guys? Did you understand this idea? We are essentially counting 1 if inside, 0 if outside. So we are essentially counting this. All good? All of you understood this, guys? 1 if inside. Yeah, you can also do that. Are you talking about the Srini? Are you talking about the subset one?
I'm talking about this as for the disjoint things A and B.
Yeah. Sorry. Yeah. So, I mean, yeah. That's one possible way. But you will see that that is one possible way. In fact, if you prove it will be coming out like this. But I want to show more elegant way, one-step method. So now we will extend this idea now. So now we want two disjoint things, right? So what we'll do now is that we will copy this now and see here. So an element now. So now I am calling a coding method. So this is subset. Let's call A, and now there will be another disjoint subset B. Okay. So an element can be inside A So an element can be inside A let's call it A, can be inside B, or can be outside O, let's say. Any element can be this. So we can say 0 if outside, 1 if inside, and 2 if B. 1 if B A, 1 if B. So an element, any element. So same structure. We have an ordered set. So any element can be now 1 so let me Just give me a minute. Just give me a minute. So now any element, observe this carefully. Any element now can be inside A or B or outside A and B, because A and B are disjoint. So we are now doing the same thing. Instead of ordered sequence of 0, 1, we are doing 0, 1s and 2s. So now each of the element, the ordered sequence can have 3 options. So it's 3 times 3 times 3. Alright. So 3 to the power n. So each element or same ordered sequence has 3 options. And it can be outside, it can be either inside A or inside B. So let's take an example. Let's take a subset. A is equal to 1, 2, B is equal to 4, 5, and rest is outside. So how do you code it? So since it's A is 1, so 1 is inside A, 2 is A, but okay. Now this third element, 3 is outside, so it will be 0. Right? Now 4 is 2, this is 2. So this means the 1 and 2 are in A, 0 outside, and the set 4 and 5 is in B. So what we are doing is that essentially we are distributing all the entire subspace into 3 disjoint partitions. Just like previously we did it into A and A complement, here we are doing A, B because the A and B are disjoint, and outside A and B. You're not able to see my screen? Okay, let's see. Can you see now? So yeah, so what I'm saying is that now we have a bidirectional relationship between this also subsets, like the entire subsets distribution and 0, 1s and 2s. So observe that if A is equal to 1, 2 and B is equal to 3, 4, 5, 4, 5, we have this coding of 1, 1, 0, 2, 2. So we have 1 for 1 and 2, 1 means in A, 2 means in B, and 0 means outside. So what we are doing essentially here, we are dividing the entire sample space into 3. Just give me a minute. Just give me a minute, guys. So the entire sample space into 3 halves, 3 separate disjoint spaces, A, B, and A union B complement. Right? So therefore, did you understand now? So each element has 3 options, therefore. Either inside A or B or outside A and B. There is no other choice. So total is 3 to the power n now. Makes sense, guys? All of you understood this? Questions? Is it clear, all of you? It's beautiful, right? And therefore, the total number of the n of E, therefore, is 16, is 3 to the power 5. And N of S is therefore 2 to the power 5 for the first one times 2 to the power 5 for the second subset, which is 4 to the power 5. So probability of E is nothing but which is nothing but 343 divided by 1024. So, but we are required to find out not disjoint, so it will be 1 minus this. So this is the probability. Beautiful, right, guys? Also understood this? Did you like this problem? Absolutely. That's the whole. I'd always draw diagrams, guys. That's why I always tell you guys to draw diagrams. Visual, it's very important. Tree diagrams, very important. So thank you guys for joining. I will meet you in the next class. From mid of October, we are starting this live course. So please, if you want to enroll. And I would love to talk to you there every day. So all the best, guys. I will see you next.
No, no, where are you typing? Which is the software, sir?
It's Notion.
Okay. Thank you.
Questions, guys? It's paid, of course. Okay. Bye, guys, and I will see you in the next video. Very happy to talk to you guys. Bye-bye.